All right, so this is going to be our lecture on the review of the graphing and the graphing practice homework that we did last night. So you're going to want to have your graphs out, looking at your graphs, maybe have your access to your PowerPoint so that you can, or access to the notes that you took on the PowerPoint so that you can refer back to them. Just for starters, remember graphs should always be on what kind of paper? Graph paper. And graphs should never be microscopic. They should always be a minimum of a half a page. Okay, because I'm old and I can't see very well. It's really nice to do graphs in pencil, especially when we're first starting out. And as we go on, I'm going to actually show you how to do graphing on the computer and how to make data tables on the computer. But I think it's really, really important to understand how to set up a graph looking at the data and how to identify dependent versus independent variables. And so we're not going to go as far on my schedule for today as I had hoped, because it's really important that we make sure that we understand this, because I don't want you to lose points continually all semester long or all year long because you don't have good graphing skills and you can't identify dependent and independent variables. I don't want to be taking points off over and over again. Okay? So I want to make sure that you've got this. So you're presented with some data for practice problem number 1. And if you did not read the directions above it, then you would have really started out immediately struggling, because that first set of data is quantity of water and quantity of oxygen. And when I look at that without any other information, I can't decide which one goes on the dependent, the x-axis, and which one goes on the y-axis. Are you missing your homework worksheet? Yeah, would you like another one? Okay, I can do that for you today, but from now on, remember that folder that you're supposed to carry, and you got a place for everything and everything in its place, right? So you can find your work. But yours is beautifully done just sitting on your desk at home, right? Of course it is. But it'd be so much better for you if you had it in front of you right now. So now you're going to have to listen to this annoying presentation again tonight and check your graph and make sure. Because, see, I don't give weekend homework. I give Friday afternoon homework. Because Friday is still the day of the week. Right? It's Friday, like I like to call it, though. Okay, so without any other information, quantity of water and quantity of oxygen, which is the dependent, which is the independent? You don't know. They're both quantities of something. So you have to read carefully the description there, and I will read it for you. Practice problem 1. The following table shows the quantity of oxygen. You all know that quantity means how much of something, right? Quantity of oxygen that can be obtained, that means gotten, from the electrolysis of various quantities of water. Okay, electrolysis. If we look at that word and we break it apart, electro. Do you know what electro means?
Electricity.
Electricity, right? Has to do with electricity. And then cis, anytime you see SIS at the end of the word, that means the process of. And to lysis means splitting, the process of splitting. So electrolysis literally means the process of splitting something using electricity. Now, you may be familiar with the term electrolysis as a form of hair removal, where they take a little electrical probe and they touch it to a hair, one hair follicle at a time. They zap it with electricity, and then over time that hair follicle won't grow a hair anymore. It's a hair removal technique. Okay? So, if you have a really hairy face, you're a woman who grows a beard, maybe you want to get electrolysis. And there are women out there that it's a genetic disorder, or it can be hormonal. So this is saying that if you run electricity through water, you can split apart a water molecule, which is H2O. And if you split water apart, you can obtain oxygen gas, which is O2. And so the quantity, how much oxygen gas can be removed when you do electrolysis of water. So with that information, Can you now determine which is the dependent variable and which is the independent variable? Which one, as an experimenter, would you manipulate? The what? The amount of water. Okay, so we could just put down here quantity of water in grams. Make sure you're always using your units on your axes. Oh, I forgot to ask you that, is this the right place to put it?
Yeah.
Yes. Okay, so this is always going to be our independent variable. We're reviewing from yesterday. And our dependent variable goes on that axis. And so that leaves us with the quantity of oxygen also in grams. And if you wrote out the word oxygen completely, that's fine too. So if you're looking at your graph and you didn't get this correct, don't erase. You're going to redraw your graph. Because I want to see what you did originally, and then you're going to redo it. So we'll be stamping it. And maybe Mrs. Fair, you could run around right now and just make sure they have 2 graphs that they attempted and then stamp. The stamp means that I know you attempted it, and that if your second graphs are all perfect, you can get, full credit. But if you didn't even attempt anything at the beginning, then that means you're late. Okay? All right. The next thing you would do, well, right away I look at this graph, and if everything else was perfect, the graph, could I get 100% on this graph on the screen here? Because I missed something. Oh, okay. I looked at a lot of graphs last period, and a lot of them missed the very first thing that we put on our graph. Okay? Dang, I know, and that's a silly way. That already knocks you down from being 100% down to a 90. And then if you make any other problems, then you're down in the 80 percentile. So it's attention to detail that's important. Okay, scaling your numbers. It's up to you what scale you want to use. If you have enough room, you can go 1, 2, 3, 4, 5, 6, 7, all the way to 28. Your scale for your quantity of oxygen, you can't go, 2.1, 2.2, 2.3. You won't have enough room on your paper, I don't think. So I would go by 0.5 maybe. Okay. Any other questions on that? The last thing that you want to do is the other thing that you want to make sure that you do is make sure that you don't leave just dots alone. You want to smoothly connect that line. Okay. And then there were questions to answer with it. Any other questions that you guys might have? Now, if you think that you knocked it out of the park and you did just fine, you read through here, draw a graph of the data, observing all the practices of good graph construction. This includes labeling the axes, not forgetting your units, scaling each axis appropriately, plotting the points correctly, connecting the points, and giving the graph a title. Check your work. If you think you're done and you can turn it in, absolutely turn it in today. Okay?
Will you be correcting me and give me this shit back, or is it?
Yeah, I don't know if I'll get it all done this weekend, but yeah. You guys need to get feedback, or I'll look at it, I'll give it a grade, I'll turn it back into you, and then we'll grade it all together. Okay? But you can almost grade this yourself by looking at what are the things that every good graph has to have. And the big problems that I see with students are messing up the dependent and independent variables and with scaling. You absolutely do not want to do this. 3, 10, 18, 23, 28, and over here, 2.7, 8.9, because what's going to happen is that you plot your points and you get a totally straight line. If you only plot the points and that's absolutely wrong. Yes?
I skipped by 3. I put 3. 6,
Okay.
12
That's fine. That's fine. So your data points are going to fall somewhere in between, right? And that's fine. Whatever scale you pick, you want to pick a scale that's going to spread out your data as much as possible. Okay? Any other questions? Those are great questions. Yeah.
Can you do a different scale for the X and Y axis?
Yes, absolutely. Because the scale that you choose on your X and Y, the question was, can you do a different scale on the X and Y axis? Sometimes your data is on your dependent variable, really small, like 1, 2, 3, 4. But your scale for your data on the other axis, your values are in 100. So maybe you want 100, 150, 200, 250, because that's what your data was. Do you always have to start out at 0? Nope. In math you do, but in here you don't. You use your data to dictate. All right, anything else? Any other questions? So if you feel confident, you want to ask a question?
Will we be doing the other side too?
I'm not going to go over the other side right now. Later will we review? Yeah, do you have one that you're concerned about?
I just wanted to know, number 4.
Number 4, identify factors that might cause a change in the shape of the graph. Okay, so maybe your graph is going along like this, and then you get that. That's what it's saying. A change in the shape. It was looking like it was, and then we changed shapes. So something happened. We were moving at a consistent speed here, but then at this point, the speed really skyrocketed. So a dramatic change in rate, temperature, speed, something like that, out of the norm. These were kind of going at even increments. This one, all of a sudden, wow. Yes?
So, if it was talking about the change of the graph, would it also mean, if it was going up and just drop down?
Yeah. Your graph could have started up here and then, So maybe this was like growth rate of a plant. And your plant was growing fine, and then one day it started wilting. And it wilted and wilted and wilted until it was like dried up and flat on the ground. Or if you're talking about rate of an automobile moving, it's moving at a consistent speed, and then it's slowing down, slowing down, slowing down, slowing down, and stopping. Okay? So that's a really important skill to be able to interpret a graph. If you have a graph that's going like this, things are moving at a very predictable, consistent rate. If it's moving like this, you can think, well, it's gone up and down and up and down. It's probably going to continue to go up and down. So going up would be increasing, going down would be decreasing. We're going to be graphing over and over again. We're going to try to put graphs into reading and interpreting graphs, designing graphs into every unit, because it's a really important skill to be able to read a graph and gather information from it. Not just for science, but what about the stock market? The graph for the stock market, if you have years here, and if they're measuring the S&P 500, which is an index, it's done this, and then maybe, and then this, and then 2008 it went down, and then this, and this, and this, and this. But consistently over the last 25 years, it's done nothing but increase. Even though there's ups and downs and dips and twists and turns a little bit, it's the end point, even though there's ups and downs up here, the end point is still at a higher level of volume being traded on the stock market. I think of that because my dad was a stockbroker. That was like his 4th career in life. Okay? So I'm going to end this lecture here. Please feel free to watch it again, like it. Please subscribe to my channel. I want to have more followers. I'm serious. I'm so vain. And I will be putting, there's old stuff from last year up there, and I may separate it out into Zitterkopf Bio and Zitterkopf Anatomy and keep 2 different channels for you guys. But I hope this helps.